Hello everyone, my name is Naman Goyal. Today I want to talk about a profound shift happening in artificial intelligence, a move beyond simple text generation towards what we call agentic AI, often powered by advanced language models. For a while now, we have seen AI primarily as reactive tools. You give a prompt, you get a text response. But the horizon is expanding rapidly. We are witnessing the rise of AI systems that don't just respond, but act. They are both active, autonomous agents capable of understanding complex goals, planning, interacting with their environment, and solving problems with minimal human intervention. In this talk, we will explore this evolution, how AI systems are transforming from passive responders to active problem solvers. We will delve into technical foundations enabling this change, examine key operational frameworks, discuss the crucial ethical considerations, and look towards the exciting future directions this research is taking. This isn't about just better chatbots, it's about redefining human AI collaboration and opening entirely new frontiers of AI research and application. So, how did we get here? Let's trace the journey. Initially, we had text generators. Think of early LLMs like GPT-3 in its initial form. Powerful, yes, but fundamentally reactive. They excelled at generating human like text based on specific prompts, but had limited awareness of broader context or the ability to act independently. The next step involved developing deeper contextual understanding. Models became better at grasping nuances, implicit meaning within request, and maintaining context over longer interaction. This was crucial, but still largely within the input output paradigm. The real transformation is the emergence of autonomous agency. Modern systems, the agentic AI we are discussing, exhibit goal directed behavior. You give them an objective, and they can figure out the steps needed, often with minimal human guidance. They transcend the limitations of just generating text based on past pattern. And this agency often involves multi-system integration. Agentic AI isn't confined into a single interface. It can coordinate actions across different platforms, tools, and APIs to accomplish complex multi-step tasks. This ability to interact with external environments is a hallmark of this new generation of AI. This shift from reactive responses to proactive goal-driven action is the core of agentic revolution. What makes this jump to agency possible? Several key technical foundations work together, which we can visualize as layers building from bottom up. At the base, we have hierarchical planning. Instead of tackling a huge goal at once, agentic systems break it down into manageable subgoals, from high level strategic objectives to specific actionable tasks, and finally, operational execution of individual tasks. This structured approach sometimes uses techniques like recursive refinement, allows them to handle complexity and maintain coherence over extended periods. Research shows models using hierarchical planning achieve significantly higher success rates, sometimes around 45% than flat plane planning approaches on complex tasks. Building on planning is long term memory. Traditional LLMs are often limited by their context window. Agentic AI needs persistence. Specialized memory structures like episodic memory for specific events, semantic knowledge bases for conceptual understanding, and working memory for current context allows these agents to retain information, learn from past interactions, and build understanding over time. Integrating explicit semantic knowledge, for instance, has shown accuracy improvements of up to 37% on certain domain specific tasks. Next, we have tool interaction integration. This is crucial for breaking free from the limitations of internal knowledge. Agentic AI can leverage external tools, APIs, and knowledge sources, performing web searches for real time information, executive code for calculations, analyzing documents, or interacting with other software. This capability extension dramatically expands their functional range. Implementations using tools have shown success rate nearly 3 times of complex information gathering tasks compared to models without tool access. Finally, at the top, these foundations enable decision autonomy. The agent can independently evaluate situations, selects actions based on its goals and context, and decide how and when it's to use its planning, memory, and tool capabilities. It's this autonomy that truly distinguish agentic systems. Okay, we have the foundations, But how do these agents actually operate? Two prominent frameworks illustrate different approaches: React and Plan and Execute. The React framework, which stands for reasoning and action, combines these two elements in the tight iterative cycles. First formalized around late 2022, it mirrors human cognition. Observe, reason, chain of thought is often used here. Act, and then observe the result to inform the next cycle. This continuous loops makes React very effective in dynamic environments where conditions change frequently and adaptation is key. It shows strong performance on tasks requiring information gathering and multi-hop reasoning, like benchmarks, Hotpot QA, and WebShop, where React showed 31% higher completion rates than some alternatives. It also shows for better error recovery because feedback is integrated immediately. In contrast, the Plan and Execute framework emphasizes a clear separation between planning and execution. Inspired by classical AI planning, the agent first generates a comprehensive, often detailed plan and then executes it methodically, making only minor adjustments along the way. Significant replanning only happens if major obstacles arise. This approach excels in more structured, predictable environments where a good upfront plan remains viable. Study shows it can lead to more coherent solutions while stakeholder ratings sometimes 24% higher on consistency metrics in domains like urban planning. It can be more efficient if the environment is stable as it avoids the overhead of constant reasoning. So, which is better? The performance comparison shows there's no single answer. Specialized frameworks excel in different contexts. Task complexity, environment dynamism, and the need for adaptability various coherence often determine the optimal approach. We're also seeing novel hybrid models emerging through that and trying to get the best of both worlds. Context sensitive framework selection is crucial for building agentic systems. As these agents become more capable, a critical question arises: how much autonomy they should have? We need a way to manage this responsibly. The graduated autonomy framework provides a structured approach. It defines different levels of agents' independence. Human oversight. At the lowest level, the agent might suggest actions, but a human must approve every step. Direct supervision. Monitor autonomy. The agent operates more independently but requires human verification at key points or from certain types of actions. Bounded independence. Here, the agent has freedom to act within predefined safety parameters, constrained or rules. Oversight is less direct, but the boundaries are clear. And lastly, full autonomy. At the highest level, the agent operates largely self directed with minimal human interventions, perhaps only for setting initial goals or handling major exceptions. The key idea is context sensitivity. The appropriate level of autonomy isn't fixed. It should adapt based on the task risk, the action's reversibility, the agent's confidence, and the sensitivity of the domain. Research suggests these nuanced, context sensitive boundaries can significantly reduce unnecessary human interventions by as much as 64% in some studies while maintaining safety, balancing efficiency with control. The agentic paradigm doesn't stop at single agents. One of the most exciting frontiers is multi agent systems, where multiple specialized agents collaborate to tackle complex problems far beyond the reach of any individual agents. This enables collaborative problem solving. Think of a team of experts. Frameworks like MetaGPT demonstrate this by assigning specific roles, like product manager, architect, programmer within a software development process. Each agent brings unique skills or knowledge. Effective collaboration requires internal dialogue mechanisms. Agents need structured protocols to communicate, share information, build consensus, and resolve conflicts. Experiments within frameworks like Autogen show that structured direct agent to agent communication can improve task completion rates by around 37% compared to centralized approaches. Often these systems exhibit hierarchical organization, mimicking supervisor worker relationships for efficient task delegation and coordination. And fascinatingly, we can see emergent social dynamics. Complex group behaviors and problem solving strategies can arise from relatively simple interaction rules between the agents, and sometimes leading surprising and innovative solutions. Multi agent systems hold immense potential for tackling multifaceted challenges in areas like scientific research, complex system design, and more by leveraging collective intelligence. Another major frontier is embodied agency, connecting the reasoning power of LLMs to physical worlds through robotics. This requires several key capabilities. environmental perception. Agents needs advanced sensor, vision, sound, touch for real-time situational awareness. This involves processing multimodal data and understanding context-aware scenes. Physical interaction. Moving beyond just text requires precise manipulation. This includes adaptive force control and sophisticated object reasoning and handling. Spatial navigations. Agent must move autonomously through dynamic environments using obstacles, avoidance, and path optimization algorithms. Physical digital interaction. Creating seamless bridges between the virtual and material realms, perhaps through real time digital twins or augmented reality interfaces. Research here focuses on grounding abstract reasoning in physical reality. Frameworks like vision, language, action models integrate perception, language, and motor skills. Systems like SPAM, RT1, and RT2 are demonstrating impressive progress, enabling robots to perform complex manipulation tasks based on natural language instructions, with success rates sometimes comparable to specialized algorithms, but offering far greater flexibility. Potential applications are vast, from healthcare, patient assistance, therapy, to complex industrial tasks. Manufacturing maintenance is potentially hazardous environments. Embodied agency significantly expands the practical impact of agentic AI. Traditional models are often static and training. Agentic systems, especially those interacting with the world, need to adapt. Continual learning focuses on architecture that allow agents to improve over through ongoing experience. This involves several processes, often working in a cycle. Experience acquisition, gathering diverse data from interactions with user and the environment. Second, knowledge distillation, extracting meaningful patterns, principles, and generalizable knowledge from these raw experiences. Model adaptation, updating the agent's internal models or neural architectures to incorporate this new knowledge. Catastrophic forgetting prevention. This is a critical challenge. This involves ensuring that learning new things does not erase previously acquired knowledge or skills. Techniques like retrieval, augmented generation, or specialized memory helps preserve critical information. Frameworks like CAML and RLICML illustrate approaches where agents refine behavior based on outcomes and feedback. The goal is to create systems that become more personalized, effective, and aligned with user preferences over time without constantly costing retraining cycles. Experiments show agents using interactive learning can achieve 24 to 38% higher success rates on complex tasks after multiple interaction cycles compared to static systems. This makes AI development more sustainable and adaptive. Perhaps the most ambitious frontier is meta learning or learning to learn. This aims to create agents that can adapt their own learning strategies when facing new domains or challenges. Key capabilities include few shot adaptations, allowing agents to master novel tasks with minimal examples, drastically reducing training data needs. Dynamic architecture modification, enabling systems to autonomously restructure their internal processing based on the problem type, optimizing for unseen challenges. Transferable skill acquisition, learning in one domain enhances performance in related ones, creating compounding returns on learning. Hyperparameter self-optimization, models tuning their own configuration settings, automating previously manual resource-intensive processes. Frameworks like Agentverse and ILAG are exploring how agents can select learning strategies like switching between imitation learning and reinforcement learning or identifying transferable knowledge components. The promise here is unprecedented adaptability. Research indicates meta learning agents might require 40 to 65% fewer examples to master new tasks compared to fixed strategy learners. This represents a significant step towards more general, versatile, and efficient AI. While much of this is cutting edge research, agentic AI is already finding practical applications across industries. In healthcare, autonomous assistants can integrate patient history, research, and imaging to aid diagnosis or coordinate complex care plans across specialists. In finance, portfolio optimization agents can balance risk and goals, independently executing complex trading strategies across markets. In scientific research, hypothesis testing can design and conduct experiments, adapting protocols based on emerging data, potentially accelerating discovery. These examples showcase the potential for agentic systems to handle complex, multi step tasks requiring reasoning, planning, and tool use in real world scenarios. With great capability comes great responsibility. The rise of autonomous agents introduces significant ethical consideration that we must address proactively. We can group these into key areas. Agency alignment. How do we ensure agent goals remain consistent with human values and intentions? We need mechanisms for value drift prevention and purpose validation. Control mechanisms. As agents become more autonomous, how we maintain reliable oversight and the ability to intervene. This includes kill switches, defining clear behavior boundaries, and designing effective human AI interaction protocols. The paper identifies control risk at a critical category. Societal impact. What are the effects of workforce, potential job displacement, and issues of access and equity? We need to consider displaced worker transitions and ensure equitable access to these powerful technologies. Accountability frameworks. Who is responsible when an autonomous agent makes some mistake? We need clear frameworks defining responsibility, including decision audit trails and stakeholder recourse mechanisms. So we're going to highlight key risk categories: misalignment, unintended consequences, deception, and inadequate control. Addressing this require interdisciplinary effort and embedding ethical considerations throughout the design, development, and deployment lifecycle, not just an afterthought. Frameworks like values sensitive design are crucial here. This slide gives a snapshot of current research focus on publication trends. As you can see, there's immense activity in developing novel agent architectures, the core structures that enable agency. Multi-agent systems are also a major focus, reflecting the interest in collaborative AI. We are also seeing significant research in embodied AI, connecting these agents to physical world and in advanced learning paradigms like meta-learning. Crucially, ethics and governance is recognized as a vital research area, though perhaps still needing more attention relative to capability development. Overall, this landscape clearly shows the significant shift in AI research towards autonomous agency, moving far beyond traditional LLM capabilities. Looking ahead, where is agentic AI heading? We anticipate collaborative agent ecosystems, self-organizing communities of specialized agents tackling complex problems through coordinated division of labor. Human agent co-evolution. Deeper symbiotic relationships will emerge where humans and AI adapt together, refining knowledge work and collaboration. Cognitive architecture convergence. AI systems may increasingly mirror aspects of human cognition, potentially incorporating elements like emotion, creativity, or intuition alongside logic. Embedded ethical frameworks. Agents themselves might develop more nuanced moral reasoning capabilities, enabling principled decision making even in ambiguous situations. In conclusion, the emergence of agentic AI represents a fundamental expansion of what artificial intelligence can be and do. By moving from reactive text generation to proactive goal directed behavior, these systems unlock new possibilities for human AI collaboration and autonomous problem solving across countless domains. As hierarchical planning, memory, tool use, and learning continue to advance, these agents will become increasingly capable. However, this progress must be guided by thoughtful evaluation, robust safety mechanisms, and strong ethical frameworks to ensure alignment with human values. The transition from passive respondents to active problem solvers is just not an incremental improvement. It potentially is one of the most consequential developments in AI evolution, fundamentally reshaping how these systems participate and contribute to human endeavors. Thank you for attending the talk.